In this video, we are going to start exploring the functions of several variables. So we're going to start out and say z is a function of both x and y. And what it does is it maps my ordered pairs x, y to a subset D in the real plane R2 to a unique number z. The set D is called the domain of the function, and the range of f is a set of all real numbers z that has at least one ordered pair that belongs to D, such that my function x and y is going to be mapped to this z value. So I have this domain, which are domains of not just x, it's x and y, and that it's going to be mapped to, or it's going to have something going on so I get a single z value out. So it's not much different than one variable. It's just now we have two variables, but they still gets mapped to one output. Now, when we're looking at functions in multiple variables, you can see it really makes some interesting looking graphs. Here is a x squared sine y and sine e to the x cosine the natural log of y. So really some interesting graphs. So first we're going to talk about the domain of the function. So when I look at this function, which is a function of both x and y, I realize that this, because it's underneath the square root, still has to stay in the land of real numbers. Because z is a real number, we're assuming we're not going into complex. So the rules that I had before, which is I have to have the square root, whatever's underneath the square root, to be at least 0 or larger, is still going to be held, still going to be maintained. So I have x squared plus y squared minus 4 has to be greater than or equal to 0. So in other words, x squared plus y squared has to be greater than or equal to 4. Now we're going to go back to the way that we graphed inequalities back in pre-calculus 1. I know it's been a while, but when we were graphing in pre-calculus 1 and we were graphing inequalities, we would graph whatever it is. We're in the xy plane for the moment, so I have y and x. Now, we know that this is a circle centered at 0, 0 with a radius of 2. So 1, 2, all the way around, and then we're going to pretend this is like the best circle you've ever seen. What this inequality is saying is that whatever my ordered pairs are, it has to be greater than 4. So in other words, I want all the values that are on the outside or on the edge of this circle. Any ordered pair I choose inside this circle, say 0, 0. If I choose this ordered pair 0, 0, then I'd have 0 plus 0 is less than 0 plus 0 is minus 4 is a negative 4, which does not keep us in the land of real numbers. So the domains for this are going to be a little bit different than what we're familiar with. So my domain of f of x, y is going to be equal to, now this is a little bit different. We're saying that we're on the real plane, or actually I'll do it two ways. And then I have x squared plus y squared is greater than or equal to 4. Now another way you may see this is I'm going to declare x and y instead of R2. R2 just means that I'm on the xy plane, or I can use the variables x, y in parentheses, such that x squared plus y squared is greater than or equal to 4. Okay, pretty straightforward on that one. Now, let's take a look at this example. With this example, what we have back in the land of one variable still has to hold true in terms of domains. And what I mean by that is that this has to be larger than 0, because I can't take the natural log of 0 or less. So y squared minus y has to be greater than 0, strictly greater than 0. So then y squared has to be greater than x. Well, y squared greater than x, this is a parabolic shape. So I'm going to go ahead and draw this parabolic shape. This is a parabola on its side. So again, this is kicking back to pre-calculus 2 of conic sections. So this is a parabola on its side facing to the positive x direction. So here's y and here's x. And so this time I'm going to be using a dashed line. And that's because I don't have equality here. So I have to use a dashed line. Now it's also telling me that my ordered pairs have to decide which way I'm going to shade. If I'm not certain which way I'm going to shade, I don't know if I'm going to shade inside the parabola or outside the parabola, let's choose a point in the inside. Nice number to choose, so I'm going to choose a test point. So I'm going to test the point 1, 0. That's right here, so 1, 0. And I put that in and I'm looking to see if that's true. Is 0 squared greater than 1? This is false. That means I'm not going to shade inside my parabola. I'm going to shade this region outside. So that is my domain, is the outside of my parabolic shape. And I don't get to include the shape itself because it has to be strictly greater than. So again, my domain of f x comma y is going to be equal to, I can do this with R2, so I can tell you I'm in the R2 plane. And then it's just the y squared is greater than x. I can also write this as x comma y squared is greater than x. All right, let's take a look at my last one here. So everything I've held true before is still holding true. This cannot equal 0. So x squared cannot equal 0. So that's nothing new. So if x squared cannot equal 0, that means x can't equal 0. That means when I go to graph this, I get absolutely everything except for at x cannot equal 0. X cannot equal 0. So my solution to this side is both this side and this side. So my domain on this one is actually a lot easier to write. I have the domain of f of x comma y is equal to, again, I can write this as I'm on the R2 plane, the real numbers on the plane xy, and just simply x cannot equal 0, or x comma y, x cannot equal 0. There's really no way to do interval notation because we are assuming with interval notation we're only talking about one variable. So unless, of course, it is the domain is everything, there's no restrictions. If the domain is everything, then you can get away with saying the domain using the interval from -infinity to infinity. More often than not, though, when we're working with two variables, we typically don't use interval notation. Now, let's take a look at this one. We're asked for the range of this. So the first thing I'm going to do is say, okay, well, let's see where I am. Now, this has to be greater than 0. So 16 minus 4x squared minus y squared has to be greater than or equal to 0. So I'm going to start with my domain so I can figure out what my range could be. So I know that I have 16 is greater than or equal to 4x squared plus y squared. Now the only reason I did that is because I don't want to mess with the negative multiplication and change in the direction of the inequality. I could have done it the other way. Okay, so what this is, we know that from our conic sections in pre-calculus 2, we know this is an ellipse whose major axis is on the y. Because if I write this in standard form, I have 16, or I have to, excuse me, I divide everything by 16. So I have 1 is greater than or equal to. When I divide the first one by 16, I'm going to get x squared over 4 plus y squared over 16. And so this is an ellipse. And I'm going to go 4 in the y direction and -4 in the y direction and 2 and 2. I have equality, so I have this. So that is my graph. Now, in this case, I want the inside, and if I'm not certain, I'm going to do a test. I think I want to do 0, 0 as my test. So I test it, is 16 greater than or equal to 4 multiplied by 0 squared plus 0 squared, and the answer is yes. So that's where my test point is, so I'm going to shade toward my test point. So in this case, my domain is going to be this 4, is going to be this equation right here. Or you can write this equation, either one. That's going to be your domain. Now, looking at this, if this is my domain, right, and I get the endpoints, the highest x value I'm going to get is 2, and the highest y value I'm going to get is 4. So this ordered pair right here is -4, 0. This ordered pair is 4, 0. This ordered pair is 2, 0. And this ordered pair on this edge is -2, 0. So let's take a look and see what happens when I put these ordered pairs into this. So I have the square root of 16 minus 4. I'm going to start with what I think is going to be my largest one, which is 4, 0. So I think I'm going to start with this one. So that means this is 0, and then I have minus 4 squared, because that's my y part, and this gives me 0. Oh, okay. So the smallest output I'm going to get is 0, because, I'm not going to get anything less than 0 because I'm taking the square root. So then the question is, what is my largest number? Well, let's choose this ordered pair when both x and y are 0. Let's try it. So I have the square root of 16 minus 4, 0 squared minus 0 squared. That's the smallest both x and y are going to get. And, well, actually, I could use -2, 0. But anyway, let's do this one. And when I do this, I'm going to get the square root of 16, which is 4. Now, let's say that I chose this one instead. Let's say I chose this one. Okay, so I'm going to do that. The square root of 16 minus 4 multiplied by -2 squared, then minus 0 squared. But this is going to give me the square root of 16 minus 4 times 4, but that's still 0. So even though my x is the smallest at -2, 0, that is not going to produce my largest range value when I plug that ordered pair back into my original equation. My largest range value, my largest output, is 4. So the range of this, come over here, let me get rid of that. So my range of my g of x comma y is going to be equal to, and this is where I get to use the interval. I can use interval notation. And the reason I can use interval notation on this is because I have a single output out. So 0 to 4. Now, can I use the set builder? Absolutely. This is what it'd look like. I would now say g of x comma y such that my function goes between 0, so g x comma y is less than or equal to 4, curly bracket, done. Now, is it easier to use set builder? Not really, not for the range. Can I use that set builder? Absolutely you can. But if you can get away with it doing a little less, maybe you're going to want to add the range as an interval. Now remember, your range is your z values. It's your output, and your output is a singular value. It's not an ordered pair. So just something to think about. Let's take a look at my last example here, that I know in general anything squared is going to be greater than or equal to 0. So that holds true for both of these two. Both x squared is going to be greater than or equal to 0. And y squared is going to be greater than or equal to 0. And let's suppose y equals 0. If y equals 0, then z is going to be 0 squared minus x squared. And since I don't have any restrictions on my domain, my x squared could be, I don't know, the ordered pair. We could have the ordered pair of $1 million, comma 0. And of course, if I put that in and I squared it, I'm going to get a very large number. So my z value, we know for the range, it looks like it's going to have negative infinity on one end. Now suppose that x is equal to 0. Now remember, I have no restriction on my domain because it's y squared minus x squared. So if x is equal to 0, then if I take a very large or even a very small negative number and I square it, it's going to become even larger. So that means my range is going to be everything. So my range of z is going to be negative infinity to infinity. Or if I'm inclined, I can write this as z such that z is a real number, if I'm inclined. Now this is not R2 because z is a singular number. It's not an ordered pair. R2 means that we are on the plane, the xy plane. When we go to graph these, we've kind of talked about this in chapter 2, I believe, when we started graphing these, and a little bit in chapter 3. When we go to graph these in 3-dimension, it can be difficult because we talked about this when we were doing this by hand, and we talked about traces. Well, the traces are still here. So what we're going to do is we're going to think about graphing this in terms of a level curve. And what a bunch of level curves do on a plane is going to give us a contour map. So if we want to think of this as that we're going to be doing a bunch of level curves on the xy coordinate, and that the z being the positive point is going to be above the x-axis, and z being a negative is going to be below the x-axis. And we're going to graph these level curves. I'll show you how to find the level curves. So here's an example of a contour map made from level curves. And this is a topographical map of the Devil's Tower in South Dakota, which, if you are a fan of science fiction, you know that's where the aliens landed. You know, Close Encounters. Anyways, moving on. So let's find the level curves at these given c values to help us visualize the shape of what this would look like. So the first thing we're going to do is say, okay, y squared minus x squared is equal to 4. So that's our level curve. And so we go ahead and we, this is like saying this, I'm doing a trace when z is equal to 4, if you want to make that connection from our last chapter. So anyways, what this is a hyperbola. So z squared divided by 4 minus x squared divided by 4 is equal to 1. So I'm going to come over here and I am going to go up 2 in my x and my y because they're both the same thing. So I'm going to go 2 in each direction. So here's this, and then 1, 2, 1, 2, 1, 2. This has a asymptote was a word I was thinking of using, which of course I got kind of sidetracked because I started drawing it. When you are drawing a hyperbola, the cheap and cheesy, easy wheezy is from the center of your hyperbola, you go out the distance A, the distance B, you draw this lovely box, you draw the asymptotes from corner to corner of the box through the center, and then we say, okay, the y is positive. You always want to hug a positive person, and so your graph is going to go along the asymptotes, touch your box, and then go out, and it's always going to be on the positive here. It's always going to go along the positive axis. Whoever is positive is the axis you're going to hug because you want to hug a positive person. Now, I'm going to just erase bits of this, and we're going to do another one. I know it isn't asking us for another one, but we're going to do another one. So let me draw that I just erased back. So let me draw this back. And I should have gone right there. So it should have gone like that. Okay. So even though it's not asking for it, let's do another one. This time, let's C equal, I'll do it in a different color. Let's C equal 1. So I have y squared minus x squared is equal to 1. Now this has a box that goes out 1 in each direction. And so I have this box that looks like this. Have these asymptotes that look like this. And then this level curve is going to go like this. And like this. Erase my box because I don't need it. And so you can see that you want to think about this as an altitude. This is an altitude of 1, and because that was my c value, and this is like an altitude of 4, so that would be your z value. So you're 4 up. So if you want to think about this, if you were looking at this as the xy plane, my first c value was at c equals 1. So here's an altitude at c equals 1, and then of course this is when c is equal to 4. So if you want to think about this, as you go up in altitude, it's starting to go like this. It's starting to curve out. So it's kind of cool. Anyways, I'm excited. Even though my drawings are terrible, I'm pretty excited. Let's continue on to the next contour. Now this one wants us to do 3 C's. So 3 values for C. Not 3C, but okay. So I have x cubed minus y is equal to -1. So, all right, let's rewrite this as x cubed plus 1 is equal to y. So this is a cubic function, and I don't have any turns, I don't think. Not really certain where I'm crossing the x-axis except for at, well, if I put in 0 for y, that will be my x-intercept. So to get an idea of what this looks like, I'm going to cross at 1 on the y, because that would be my y-intercept if I put in 0. And then my x would be -1. And then I probably should put in at least one more value for x. So let's put in, oh, I don't know, 2. So if I put in 2 into here, I would have 2 cubed plus 1, which gives me, if I put in 2, I get 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And I have 2. So this is my first one. It's going to look something like that. And I'd probably, since I'm graphing this by hand, I'd probably choose a couple of more ordered pairs to put in there. My second one is going to be, so I'm going to do this in red. I have x cubed minus y is equal to 0. So x cubed is equal to 0. So here it's going to go through 0. This is a cubic function. If I put in 1, 1 comes out. If I put in -1, -1 comes out. If I put in 2, 8 comes out. So it's going to be like right there. And so that's this one. So that's that curve. And then I'm going to do my next one in blue. And I have x cubed minus y is equal to 2. And so I have x cubed plus 2 is equal to y. So I'd put in the ordered pair, oh, that should be -2. It's like, what? Okay, that's -2. So I put in 0 for x, and so a -2 comes out, so it's going to be down here. So here's -2. And then my y is, when my y is 0, my x is equal to the cube root of 2, which is, about right there, less than 1. And then I would put in some x value. So let's put in 2. If I put in 2, then I'm going to get, this is going to be 2 cubed minus 2. So I have 8 minus 2, which is 6. So when I put in 2, 6 comes out. And so that's what that looks like. So you can see it's a bunch of curves, cubics, and I'm sure I'm probably not drawing these very well, but that's what that would look like. And this, again, is starting to build my contour map. So let's do this next one. We're going to go ahead and put in c is equal to -1, 0, and 1. So I have h of x comma y. I am going to set this thing equal to -1. So I have the natural log of x squared plus y squared is equal to -1. So a little bit of algebra here. So I'm going to take e raised to both sides. And I'm going to get x squared plus y squared is equal to e raised to the -1. And so what I end up with is an ellipse, or actually it's a circle. So my first circle has a radius of 1 over e, the square root of that. To make my life easy, let's call this going out 2 in each direction. This is going to be, let's call this ordered pair, I'll write it down here. This ordered pair is going to be 0, 1, the square root of 1 over e. And so here's my first one. Now, when I do this again, I'm going to have, again, x squared plus y squared is equal to e to the 0. So this is 1. So let's have this be 1. So here's this one. I'm going to do this again where I've got the 2. So I have x squared plus y squared is equal to e raised to the 1. And so there's my last one. So I have a bunch of circles. So if I were looking at this, so this is the xy plane. What's happening is that here's my z-axis. As my z's increase, so here is z at -1. As z increases, my circles increase. So it's going to look something like that, which is pretty slick. Okay, moving on. Now we're going to have vertical traces. This will also help us graph. Now, it's exactly what we expect. It is the vertical trace. And we graph these in either the xz or the yz planes if we are looking at the vertical traces for x is equal to a number or for y is equal to a number. So it depends on which direction we are going. So let's take the vertical trace of z is equal to 4 minus x minus y. So I have a replacement for x, and so I have z is equal to 2 minus, I got so excited there. It will be 2, but it is 4 minus 2 minus y. So in other words, I have z is equal to 2 minus y. Now, if I consider this my z-axis and I consider this my y-axis, then what I have is I have this line on the xz plane, that's parallel to the xz plane, of -y positive 2. So here's positive 2, and it has a slope that is negative, so it's going to look something like that on the yz. And of course, we remember that x is actually coming out in this direction, so that would be at x is equal to -2. So it would form a line on the graph, the plane at x is equal to 2 on that plane. It's going to form that line there in red. This is my x-axis. Okay, so for this one, I have the cosine of the square root of x squared plus y squared, where I'm going to be putting in x is equal to 1. So z is equal to the cosine of 1 plus y squared. Now what I know is this is going to be a cosine wave, so here's z and here is y. So this is really a really ugly way of saying the cosine of theta. So it's going to be a cosine wave. What is going to change is not the altitude, the amplitude of it. It's going to change the period more than likely. But I am going to have a cosine wave. I'm assuming I'm going to start in my usual cosine wave. And so it's going to look something like that. And I would probably find some, I'd find the period. So I know that I'd have to find the period my usual ways back in pre-calculus 2. Or I could just plug in some points to get a good idea of what this looks like. And that's what the trace would look like. Now, again, I am actually looking at the trace at x is equal to 1, so the plane. So on the plane, which is x is equal to 1, the trace would be this cosine wave. We can also find the domains of functions that have more than just 2 variables. And it's not going to be anything different than we did before. We have 2 things that are going on with this example. First of all, we can't have it because it's underneath the square root. This cannot be 0. It has to be greater than 0. And then because it's in the denominator, it has to be strictly greater than 0. So I have 36 minus 4x squared minus 9y squared minus z squared has to be greater than 0. So strictly greater than because it's in the denominator. So let's go ahead and move everything but the 36. So I have 36 minus is greater than 4x squared plus 9y squared plus z squared. And we know this is an ellipsoid in 3 space. Here's my z, here's my x, and here's my y. Now, if I want to know what this would look like, I would probably do the trace in each one of these. So if I let this equal 0, then the trace in this direction would be the x would be larger than the y because it would divide both sides by 36. And so I would have x squared here. And let's do the trace in the xy plane. So z is equal to 0. So on the test, so let's take a few moments to make sure we are comfortable with this. So I have 36 is greater than 4x squared plus 9y squared. And so I have 1 is greater than x squared over 9 plus y squared over 4. So in this case, I'm going to go here in the x 3. So here's 3 and negative 3. In the y, I'm going to go 2. So negative 2 and 2. So this is what that piece kind of looks like, terribly drawn. I had this professor and when I was taking Calc 3 back in the Stone Age. So I'm going to give a shout out to Rudy Gunawa. And I had a moment of like, I knew his name and then it lost me. He retired, of course, years ago, but if any of you had him or know of him, shout out to him. He did some of the best drawings by hand with chalk and a piece of string. Anyways, moving on. So now I'm going to do my trace in the y, or the yz plane. So that means x is equal to 0. So I have 36 is greater than 9y squared plus z squared. And so 1 is greater than y squared over 4 plus z squared over 36. So in the z direction, I'm going to go 4. So here's 4 and here's 4. And so my y is still 2, obviously. And so it's going to have some sort of ellipsoid that's kind of like this. Something like that. Not drawn well, not shaded well either. Anyways, so we go back to the fact that this domain has to be such that I am contained within this ellipsoid. So it's going to look something like that. So there's my ellipsoid, and it's going to have to be contained because it has to be less than. It has to be less than the 36 or less than 1. And so my domain for this 3, so my domain of my function, which is x, y, and z, is going to be equal to, and now I can write this as R3 because I'm in R3 space. And then I would tell you all about it, and I would have, let's do it with 1 this time. So dividing everything by 1, I've got 1 is greater than, strictly greater than, and it would have been x squared over 9, and I wrote 6 because I was thinking of 36, x squared over 9 plus y squared over 4 plus z squared over 36. And of course, I can also write it this way with my ordered triplet x, y, and z. And then y1 is greater than x squared over 9 plus y squared over 4 plus z squared over 36. Okay, so that is the domain for that one. Let's take a look at this domain. Now, let's just talk about this. It's a cube root. Because it's a cube root, I can have positive and negatives underneath the square root. So it doesn't matter what I choose for x, y, and z. They could all be 0 and I'm cool. One could be 0 and the other two could not be 0, but it doesn't really matter because of the fact that I have a cube root. So this is one of the ones where I get everything. So my domain of my f of x plus y and z is going to be, well, this is one where I have no restrictions on anything. And because I have no restrictions on anything, then I can write the domain of this as just negative infinity to infinity. There's no problems there. But the way that we do this is we write it as R3. So that tells me that any value for x, y, or z is going to be okay to have. That's how we do negative infinity to infinity. If I have, for all of them, if I was in 2 space, the domain of f of x, y in 2 space, and I have no restrictions, would be R2, something like that. Now let's talk about graphing in 3 variables. So a function of 2 variables has level curves, which we've done, and they're on the xy plane. When the function has 3 variables, then we have curves that become surfaces. So we define level surfaces for functions of 3 variables. So given a function f, y, and z, the number c is in the range of f, then remember this is the output that I'm choosing, then the level surfaces of a function of 3 variables is defined as a set of points satisfying this equation. So even though this doesn't seem like it's in 3 variables, it really is. So this is z is equal to 2 minus the square root of x squared plus y squared. So the first thing we need to talk about is the domain of my original function. So I'm really talking about f of x, y, because I need to know what I can put in so that when I try to do my level curves, I know that I'm choosing valid choices for c. So first thing is, this is underneath the square root, but because it's underneath the square root and they're both positive, and I'm adding 2 positive numbers together, at a very minimum I have 0, right? 0 plus 0, which is totally okay to square to 0. Because of the fact that I have x squared plus y squared, and they're both positive and they're both being added together, that my domain initially is all of R2. I don't have any restrictions on that. Now, the other thing that we get is what would be the output, because we need to think about this, is that we have some c, which I have 2 minus the square root of x squared plus y squared. So could I put in c being 5? Well, no, because if I try to put c's 5 right here, then I'd end up with something like this. I would have 5 minus 2, which is 3. 3 is equal to negative x squared plus y squared, and 3 is never going to equal a negative number because the square root is going to be positive. So this is going to be a false statement. So that tells me the largest output, my range, this is where it's kind of important, my range values are going to go from 2 and then less. So my range of f of x comma y is going to be equal to negative infinity to at the very most 2, because I'm subtracting off a positive number, and it can be a very large positive number. So that's my range. So that tells me that my c values have to be at most 2. Okay, cool. So let's just rearrange this a little bit to see if we can figure out what the shape is without having to actually do a bunch of c values. So let's rearrange this. Let's write this as x squared plus y squared is equal to, and then what I did is I added the square root to both sides, and so this would be 2 minus c. Let's square both sides, and I get x squared plus y squared is equal to 2 minus c, the quantity squared. Oh, look at that. That's a circle. So a circle centered at the origin, whose radius is going to be 2 minus c. Of course, we end up with c values. When we choose our c values are negative, it becomes positive, so don't worry about it being a negative radius. That's not going to happen because all of my c values, remember, are negative infinity to 2, so I couldn't put in 3 or anything here for c because, I couldn't do a negative radius. So the biggest I'm going to put in is 2. So we have a bunch of circles that are centered at the origin, and they're just going to be concentric circles. Now remember that the 2 minus c is the z, because we're in 3 space. So what I'm really trying to graph is x squared plus y squared minus z minus 2, the quantity squared, is equal to 0. And you're thinking, wait a minute, isn't that 2 minus c? Well, yeah, it is 2 minus c. But this tells me the very largest range value I can get, which is 2, and that is my z. So that is the largest range value, which is 2. So basically what I have, if I were to do this on the xy plane, I have a bunch of concentric circles for each c value I choose. But these are coming from the z-axis. So what's happening, because my z values are, if I'm looking at this being my z, then my negative z, I don't get to start until positive 2, right? Because that's the biggest I get is positive 2. And then I'm going to have these circles, right? So these radiuses are going to expand out like this. Each of my circles that are running parallel to or on top of the xy plane. So I end up with this shape here. And then of course this is my x-axis. So I have this paraboloid, and it's going to be facing downward, and it's going to have the z value has to be shifted up 2 because that's the best you're going to get. That is the highest range value, the largest range value you're going to get. I'd recommend you check that, but that's what it's going to look like. It's kind of slick. And then here's my last one, which is z is equal to 1 plus e negative x minus y, negative x squared plus y squared. Again, let's talk about the domain first so I know what I can and cannot put into my x and y's. Now, e raised to any power is always defined, so my domain of my z here is going to be any real number in the x or y plane. That's not necessarily going to tell me what my range value is. And of course, I want to know what this shape looks like. So I think what I'll do is I do before is rearrange this a little bit. So I'm going to start out with saying c, because that's what the z value is. 1 plus e raised to the negative x squared minus y squared. Now, we know that this is the same thing as c 1 plus e negative x squared plus y squared. Just factoring out that negative. X squared and y squared are both positive numbers. So the smallest I'm going to get if I put in any value for x, any value for y, is when x and y are both 0. So c would be 1 plus e raised to the 0, so that gives me c is equal to 2. So that is the largest value I'm going to get. It's the largest value. Now I want to know what my smallest value would be. Well, c is equal to 1 plus e raised to the x squared plus y squared. As x goes to infinity or negative infinity, so let's do it together, as x goes to positive or negative infinity, then I'm going to have e raised to a very large negative exponent, which makes it almost go to 0. And if y goes to positive or negative infinity, and it doesn't matter if it's positive or negative because we are squaring it, then what ends up happening for that is also e raised to a very large magnitude-wise of a negative number, so a very small number. And so what ends up happening is that as x and y go to either positive or negative infinity, because it can take on any value, that pretty much this term goes to 0 as those get larger. So my c value is going to be 1, but it's never actually going to get 0. So it's going to be, for all intensive purposes, it will be 1, but it's not truly going to be 1, because I don't really truly get 1, because I'm always going to have some residual from e raised to negative 1 million or whatever. So I'm going to have something left over. It isn't actually 1. I don't actually get there. So the range of my z here is going to be from 1, but not inclusive, up to 2, which is inclusive. So those are the best c values I'm going to get. So since these are the best c values, let's talk about what I could choose and go ahead and do that, what the shape would look like I did before. So I'm going to go ahead right here and take 1 to the other side. So I have c minus 1 is equal to e raised to the x squared plus y squared. Now I'm going to go ahead and do the natural log of both sides so I can bring that exponent down out front. So I have the natural log of c minus 1 is equal to the natural log of e raised to the negative x squared plus y squared. And again, the reason I'm trying to do this is I'm trying to figure out what the shape would look like so that I can make my life a little bit easier by not just arbitrarily choosing values of c and trying to solve. So if I can have an idea of what the shape looks like prior to, it's going to make my life a little bit easier. And so I end up with the natural log of c minus 1 is equal to negative x squared plus y squared. So let's go ahead and bring that negative to the other side. So I have the negative, the natural log of c minus 1 is equal to x squared plus y squared. And now I'm going to use my laws of logs and bring that negative 1 as an exponent, the natural log of c minus 1 raised to the negative 1 is equal to x squared plus y squared. And so I end up with the natural log of 1 over c minus 1 is equal to x squared plus y squared. And this kind of looks like a circle equation again, which it certainly is, where my radius is going to be the square root of the natural log of 1 over c minus 1, where my c can only be from 1 to 2. So once again, what I have is a bunch of circles, concentric circles on the xy plane. And it's going to look something like this. So we're back here on the xy plane. And I'm going to have these concentric circles centered at the origin, where at the most, I'm going to have my c value that can run between 1 and 2. And so I'll have a bunch of concentric circles. What does this look like in 3 space? Well, again, here's my z and here's my y. It's going to look something like this. It's going to have like, I don't know, it's going to be, so at z is equal to 1, but not inclusive. You can have like the concentric lumps, circle-like things all the way up to 2. Just not drawing this very well. And then, so it's just going to be like this mound. It's going to be like a mound, but it's not going to, unlike our other shapes that keep going down forever or going up forever, whatever, this is going to be a mound that's going to max out at 2, and then it's going to be constrained by this plane where z is equal to 1. So you're going to have this constraint on this mound. It's really hard to graph this by hand. I'd recommend you consider drawing this. This is my x-axis. I'd have you consider doing this graph in a graphing utility that does 3 space, so you can really get a feel for it. It's kind of like a mound though, which it's like a lump. It's like a, I don't know, an infinite bowl, sort of upside down hat. I don't know. Hard to say. Anyways, that's it. So the next section, we're going to start doing the calculus of these. Yay! We're excited. That's it for today.